Hello, welcome to another video on Science 10. Today we're going to start looking at Unit D, which is the energy flow in global systems. We're actually taking all we have learned about biology, physics, and chemistry. Not all of them, but like a little bit of everything, and look at the bigger picture. And here we're looking at the energy flow within, what's really all about, the planet we're living on, which is planet Earth. A globe system revolve in our what we call a biosphere. Okay, so we're taking a look at our focus for the next little bit is going to look at the how the globe energy flows in the biosystem, and look at how it has impact on our lives, on our climate, and our temperature, and all that, and weather. So let's just begin to put everything into context. So we're going to take a look at our biosphere, okay? And the biggest thing one thing we really care about biosphere, well, really two things, is the weather and climate, okay? So let's make a very clear distinguishment in science. Climate and weather are actually very different things, okay? So before we begin, take a look at this two picture, okay? Well, they are technically not the perfect representation, but if you're going to look at this, what's going on in these two pictures, which best represents a scenario describing a weather condition, other one describe a climate condition, like metaphorically, I guess. Okay, metaphorically. Okay, give it time to think about it. You can pause the video and come back. All right, hopefully you pause the video and think about it. Which one really best describes climate, represents climate, and which one best represents weather? Well, at least the intent was the first one, the top one represents weather, right? There's a tornado going on. Okay, that doesn't happen every day. It doesn't happen over a long time. If your tornado is happening right now, that's the weather. Okay, hey, there's a tornado outside. There's a thunderstorm outside. It's raining outside, or it's minus 40 outside. It's really cold. Okay, during some of the Alberta winters. Okay, it's really cold outside. It's minus 40. That is weather. Okay, things mentioned here: temperature of the time, air pressure of a time, cloud cover, precipitation. Okay, all those stuff. Okay, but the key here is not we are measuring for climate, we measure exact same thing, but for weather, we determine them at a particular place, a particular time. That's why my example says Alberta, or well, we need to be more precise. Really, it's Edmonton's in the month of December of 2019. It was minus 40 degrees outside. Okay, really cold, and it was snowing. Okay, it was dry snow. There you go. That would be description of weather. While climate is the average weather over a long period of time. We're still studying temperature, air pressure, cloud, all that stuff, precipitation. Okay, but it's over a period of long time. Okay, at least 30 years. Okay, now if where you live have tornadoes, okay, every single year during the same time for all 30 plus years, then we will say tornado will occur during this month every year, right? Tornado expected around this month for your climate, for your region. Okay, that would be now a climate statement. So that's why I say that photo might not be the best representation, but tornado is an expected weather for your climate. Do you see a difference? Weather is a specific condition at a specific time, while climate is long range. Okay, weather is only a small part of what climate is. There's often that confusion if you go online or if you look at some discussions regarding what's a heated topic right now is global warming and the climatic change. Okay, and then there is often this confusion between climate and weather. Climate is long term, weather is short term. You may have a cold winter for 1 year, but overall, that it is possible. It's the climate, okay, is towards is increasing in its temperature. All right, but we're not going to quite jump into climate change today, okay, or this lesson. We're going to look at that once we develop a system where what we're working with. What is the Earth all about? So, Earth. Well, this is a picture I got. Well, I found on the. I found. Okay, not on the interwebs. It was shared with me. But it's not my photo, but it's just a picture in the Rockies. Okay, it's quite beautiful. There's water here. There's a giant lake. You see the clouds in the sky. You see the mountains, of course. You see the trees. And this is a perfect image of what the part of Earth we actually care about. Okay, the part of Earth we actually care about, where life exists. Okay, and that, okay, is what we call the biosphere. Okay, biosphere. So all the stuff, the weather and the climate, the stuff we'll be taking a look at happens in our biosphere. And biosphere is the part, okay, I'm going to highlight this one. This one is that it has conditions suitable to support life. Okay, that's really the part we care about. We don't care about outside of the biosphere. Bio, it's if you're in biology, study of life. Biosphere, the sphere where life exists. Okay, I'm sure that's a part you would care about. That's where we live. So that's going to be our focus, is how the energy going to interact within the biosphere, both chemically and through the physics, biological and chemical concepts, just a little bit, and how the energy transfers. Okay, and of course it's made up of 3 parts: the atmosphere, the air, not include the cloud. Okay, if you may remember, cloud is not actually air. A cloud is made up of mixture of gases. We call them air. Okay, I'll take a closer look at what they are. The hydrosphere, of course, which is the water, and the part where, well, humans live on, which is the lithosphere, which is really the Earth. So air, earth, and water. That's what we're looking at. Energy, and all of these, okay, the original source of energy came from the sun. There's a little caveat. It's actually 2 things. I do want to mention it, is because it will pop up later, is that I need the lighter color. There is also, in bracket, also geothermal energy from the Earth. Geothermal as well, but not as much as the sun, but still vitally important. So I would like to mention it here. Geothermal, which is energy from the Earth's mantle. Okay, energy from the raging mantles inside of the Earth, lavas and stuff like that, and even more energy from mantle, which in turn you can say came from the core. Okay, so there's also geothermal as well. So energy from the sun, this is primary, is secondary if you want, which we will not focus on as much because vast majority came from the sun. Okay, vast majority primary. All this energy came from the sun. If you remember, we talked about open, closed, and isolated systems. Okay, for most scenarios, we treat Earth as a closed system. If you remember, closed system is where matter exchange doesn't happen, but energy exchange happens. Yes, we send people and dust and garbage to the space all the time, but those are minuscule compared to the energy and the space, no pun intended, that the Earth and the sun and it takes up within our universe. So we consider Earth a closed system because there's energy exchange. Energy from the sun comes to Earth, and Earth's thermal energy also released into space as well, include also, of course, reflected sun rays. So there's energy exchange between Earth and space, specifically the sun, but not matter exchange. So we usually treat Earth is a closed system, which means if you want, it's okay. Earth is almost like the joke, like Vegas. What happens on Earth stays on Earth, at least in terms of matter. So okay, so things like we'll look at, but spoilers, I guess. Things like pollutants, okay, dirty air particulates, okay, or even good things as well as like things we very importantly need, like air and water. Okay, those things tend to stay and be trapped, by a gravity of Earth, and as well as the corresponding energy exchange. So Earth is a closed system. Okay, so just remember though, I want to emphasize, closed doesn't mean there's no energy coming in. Energy is still being fed to us. So the second law of thermodynamics doesn't quite apply perfectly. Okay, Earth is not falling apart. Okay, that's what second law predicts. It's not falling apart because we're receiving energy from space to do the things we're gonna study right away. Okay, so a little bit of energy transformation review. All right, let's take a look at the layers. Okay, let's start with maybe the one I think is probably the we want to think about the most and we interact with the most, with the lithosphere. I'll keep it simple. It's just a solid portion of the surface of the Earth. I'm going to add it in. Surface of Earth. Oh, I forgot to change the pen color. Of the solid portion of the surface of Earth. We do not care about subsurface stuff. Okay, like those below ground, the mantle and the core. That's not our focus of the biosphere. We have trivial amount, like tiny amount of life I'm not even aware of really living in those conditions. Most of life living in our biosphere. So the surface of Earth is composed of rocks, minerals, and various elements. Okay, it ranges usually around 100 to 200 kilometers thick. Okay, and it floats. It's not a exaggeration. It is floating on this mantle. Okay, it's floating on the mantle. Okay, which is not about part of a biosphere. Okay, biosphere is only a surface. Okay, and the life is found to depth at several kilometers. Okay, so you can indeed find life still in there. There are some extreme circumstances of mountains, of course, you get a little bit thicker. We'll look at some examples, but usually it's the lithosphere is really thin. Okay, to borrow a quote from Neil deGrasse Tyson, if you are a giant, a spatial gigantic giant, bigger than the sun, and if you're going to hold the Earth, like Earth is to you is a basketball. Okay, Earth is like a basketball. Okay, if the Earth is the size of a basketball, if you touch the surface, the basketball surface is going to be more. It's going to be more rough or rougher, whatever, or rougher than the Earth's surface. That's how thin the lithosphere is compared to the Earth's radius. And you'll see Earth's radius is 6,000 kilometers, while Earth's lithosphere is usually around like 100 to 200 kilometers thick. Okay, rare exceptions, but that's not very thick compared to 6,000. Okay, so yeah, it's not very thick. Remember, our tallest mountain, which we're going to look at, okay, tallest mountain is only 8 kilometers above sea level. Okay, it's only above sea level. Yes, you should technically account for the depth of the sea as well, but still, that is still nowhere close to 6,000 kilometers. That's 6 times 10 to more than 6 times 10 to the 6th meters thick. Okay, and this is only times 10 to the 3, 1,000 times. Okay, so it's really, really the biosphere is really thin compared to what Earth is. Sorry, it's just so cool about these numbers that which is so cool about these numbers to show that how small our living realm really is. So have a tiny house if you want to think about it. The universe is a giant uh, space. We only live in a tiny house on that giant space, but we're tiny too, so we don't need too much space. Maybe. Uh, Technically, we only consider the lithosphere, which is the land where land creatures live. We do not consider the under ocean part, where also animals live, considered as part of the hydrosphere. So consider that. The lowest point on Earth, on the lithosphere, um, is the Dead Sea, which is 399 meters below sea level. Okay, that's the only location among the lithosphere we consider. We don't really consider the part of the crust that's below the sea. Okay, because that's part of the hydrosphere. Okay, so above the, it's not sea level so much, but above water. Okay, so these are two extremes on the lithosphere. Okay, so that's the land we live on. Some data about the land we live on. It's very thin, but that's where most of our activities occur. Another big thing, okay, of our biosphere is of course the water we drink, and of course the water cycle that helps transfer those energies and keep us alive. Oh, sorry, I'm skipping ahead myself. I'm too excited about the hydrosphere. The next one is probably slightly more important than our hydrosphere, but the very air we breathe. Okay, very air we breathe. So the atmosphere, a thin layer of well mixed gases. We have a name for these gases. Okay, have a good guess what the name of those gases is. Oh, wrong. Oops. No spoilers because so well mixed gases. Okay, atmosphere is a well mix of gases. These gases are called. Let's play Jeopardy here. Okay, pause the video for the length of a Jeopardy song and then come back. What is it? Do you know what these gases are called? And if your guess is, oh, hope you did try it. It's called air. It's right here. Okay, air is not gas. Okay, it's a special type of gas. The gas on Earth's biosphere. Okay, that's what we call air. Okay, so a thin layer of air, if you want, surround the Earth. Okay, this one is much thicker. Okay, it's much thicker. It extends approximately 500 kilometers. It is still less than 10% of the Earth's actual radius. Okay, it's still very thin, but yeah, but it's definitely thicker and probably noticeable. If it's solid, we probably notice it more. If the Earth is basketball. Okay, so it extends approximately 500 kilometers above the surface, and here are the most primary composition of the gas. Maybe you know already, and these are the composition of the gases. So nitrogen is the most, about 78%. Okay, or not exact, right? Oxygen is about 21%, and remaining about 1% are trace gases like carbon dioxide and water vapor. Okay, they're only a small amount. And then there are dust particles. We actually call them atmospheric dust or atmospheric particles. That's a mouthful to say. Atmospheric dust or atmospheric particles. If I saw those words or give you in the question, you know what they mean. It's pretty obvious. It's particles floating in the atmosphere. They are usually solids. They could be organic or non-organic. Like inorganic could be like soot, or like rock dust or like floating sand particles. Or it could be organic, right? Like pollens, right? So those are all considered dust particles, atmospheric dust. Now you might think, hey, there's a trace amount of gas. Do they not contribute? First of all, think about how big the Earth is and how thick the atmosphere is. Now, it is true it's not evenly distributed, as we'll see later. Those trace amount of gas still have a huge impact on our climate, even a small amount. If they have If there's as much carbon dioxide as oxygen, our planet would not be survivable at all. So if you look at the layers, okay, this is a layer of atmosphere. Atmosphere is so thick, we actually able to divide them up into four spheres as well within atmosphere. We have the outermost called the thermosphere, most satellites fall there as you see, and then the mesosphere or mesosphere. The stratosphere is where your plane usually flies, and the troposphere. Uh, Pronouncing these spheres, so many spheres, is making it really hard to say them. Okay, I give up. This innermost sphere, okay, is where we live in. Okay, it's innermost. As you notice, it's only a small part of the atmosphere we actually live in. So let's focus on the small part we live in first. We, as in the humans, okay, there are creatures who can go live in almost outer space in the thermosphere. Anyhow, in the troposphere, this is a comfortable area to live in. The average temperature is 15 degrees. Very comfortable, not like warm, but it's livable. But it could go down to like minus 60 degrees as altitude increases. Okay, if you climb the mountains, temperature get close. That's why you come on to Everest or even just the Rockies. You gotta dress really warm. Okay, the peak is usually covered in snow, all for all seasons because temperature is really low as altitude increase. Okay, so remember, if I want, it's like temperature. I'm going to use T for temperature. I don't want to use T per se because T does mean something in physics, but it is the best unit we got, so I'm going to use capital T. Goes down. As altitude, we do not use A. We use height for obvious reasons as altitude increases. Okay, so that's what happens in the troposphere. It contains 80%. It is not very thick, okay, but it contains most of the atmospheric gases. Okay, I'm gonna want you to think about. I'm not gonna tell you why. Think about the things we have learned so far. Why do you think most of the air is closer to the Earth's surface, and there's way less air out there? Okay, way less out there. Why? Question mark. Okay, think about it. I will not give you the answer away, okay, but really think about. I think it is a concept we discussed in physics, but you have been experiencing it every single day, okay? So why do you think 80% of the atmospheric gas is near the surface while there's less out there? Okay, if you think of gases as like actual particles with mass and weight, it probably makes more sense. That's a hint. All right, so it includes a higher concentration relatively, okay, of O2, okay, which means it supports life, which we use O2. If you remember in chemistry, O2 is required for a lot of processes, specifically for combustion, digestion, and all that, right? It's very important for many chemical processes. Important. For the chemical process you have learned, you'll learn more of it in Chemistry 20, but we're not going to dive in more than that. Like the digestion of your food and burning of your fuel all need oxygen. So that's why life exists in the bottom half, not in the middle, even though they do exist. Then we're going to look at our neighbor, which is the stratosphere. We don't live there, but we do travel there relatively often. It's something called an airplane. Okay, there's almost no air up there. Okay, it's almost very thin amount of air up there, and it's pretty cold, I just say. But not too cold. In fact, it went from -60. Remember, that's coldest of the troposphere, and it went back up to 0°C. Actually, for this area, I'm use different color. For the stratosphere, temperature goes up as height goes up. Okay, so near the top of the stratosphere is actually pretty warm. It's around 0 degrees. Okay, 0 degrees Celsius. Okay, quite interesting. Now this is a layer your airplanes flies in, right? Airplanes are here. Usually flies here, not all of them, but most of the commercial jets international jets do fly in this region because there's way less air resistance. Okay, so you can maintain the speed to keep it flying. Airplane flies here. Okay, so it contains something called the ozone. The ozone layer is in the stratosphere and it absorbs a quite amount of high energy radiations. Okay, not solar radiation, light radiations or electromagnetic radiations, UV, X-rays, and gamma rays. I do want to specifically say electromagnetic radiations because the solid particles, the solar wind, okay, charged particles actually deflected later. So these one are more penetrating. They actually penetrate. Some of them do penetrate the first layer of protection, which you'll look at. But much of the dangerous radiations, the UV, X-ray, and gamma rays, actually gets absorbed, okay, by the particles, okay, and then released or reflected backwards into space. So that protects us living organisms. We won't get strange mutations and damages to our body and to our cells. So that's the stratosphere. Next is the mesosphere. Ranges from 0 degrees at the bottom to minus 100 degrees at the top. Once again, for the mesosphere, spoilers, temperature goes down as height goes up. Flipped around again, very much like our troposphere. Interesting. Okay, so that there is nothing too interesting here except that temperature fact. This okay. Well, one thing is interesting. You can live up there. It's really cold. Okay, it contains coldest temperature on Earth, and there's no actual breathable air up there. There's trace amount of oxygen, and there's no lithosphere. Lithosphere does not go that high. Okay, it's 50 to 80 kilometers in width, and finally, from 80 kilometers to about 300 kilometers and upwards. Okay, 300 kilometers upwards. Well, that is the thermosphere. Okay, this contains the hottest part of the temperature. In fact, a temperature goes up as height goes up. Okay, a temperature goes up as height goes up. Okay, flipped again, very much like our stratosphere. How interesting! It ranged from negative 100, some of the coldest temperatures on Earth, minus 100, to 1500 degrees. Great. That's like burning, more than burning. Things are melting around those temperature. Very interesting. Okay, this is our first layer of protection. Okay, this is where auroras happen. Okay, there is technically something called an exosphere. We're not counting that. Like there's are still within the Earth's gravitational pull, and there are some atmospheric particles in there, but we don't usually account for them. Okay, but that's still part of Earth. We'll not discuss them too much. But thermosphere is usually where let me draw some aurora there. Auroras happen. So aurora, there we go. Okay, aurora usually happens here, and planes usually fly in the stratosphere. Let me draw that airplane. Stratosphere is right there. Plane. And of course, people live down here. Stick figures live in the troposphere. Okay. Now you realize humans are not that big. Okay, and we are in fact like the area we live in is tiny compared to the biosphere. Now, what are aurora? Someone even already know. It's the ionization of air molecules in the higher levels in the thermosphere. Okay, bombarded by solar winds. Solar winds actually are particles ejected from the sun because not chemical reaction, but the nuclear reaction with the sun releases so much energy, actually shoots a piece of the sun into the air called a solar wind. That piece of solar matter ejected at Earth at high speed. They are charged. Okay, and then Earth's magnetic field is deflected, and as it passes through, it doesn't hit us head on. As it passes through the Earth's thermosphere, okay, it hits some small R particles, and those R particles release light, okay, and those are going to be studied in physics. Are those going to be studied in physics 30? So I'm not going to talk more about how it works, but the fact it does work. Okay, so solar wind hits some air particles in thermosphere and then becomes auroras. Okay, if those solar matter hits Earth, it's going to cause massive damage to our biosphere. So thermosphere does, in fact, well, not the thermosphere, but the Earth's magnetic field does protect us against those charged particles. Okay, not the light particles, which are not charged. Okay, but I'm going on tangent. There's so many cool stuff about our planet. Some images of the aurora borealis, and if you got a chance to go out during winter, you might actually see some of them in Alberta. All right, so remember we have talked about the temperature. This is one of the coolest things or most interesting things about our atmosphere is that if you notice in the troposphere, temperature goes down. So this is colder. I'm gonna highlight this is cold because temperature is in the negatives, and this is hot. I don't think I have to say this is low, this is high. Okay, so in the troposphere, temperature goes down as it goes up. But in the stratosphere, it goes up. The temperature increases as increasing height. Temperature goes down again in the mesosphere, and then increase again in the thermosphere. Okay? Oop. How interesting, right? How interesting. Why do you think that's the case? Okay? Why do you think that's the case? Okay, just quick summary. Atmosphere does get thinner as we move away from Earth. The thickest part at the equator, the troposphere is the thickest at the equator and thinnest at the poles. Okay, think about once again. Think about why. Why? You might do a little bit of research for that though. Okay, but you need to know the first question first. And the troposphere temperature decreases with altitude. Okay, so the higher mountains, right? It's usually snowy peak, and it's warm down here. Okay, nice and warm, snowy peak, and the colder near the top. But if we move beyond troposphere, temperature drops, but in stratosphere, temperature rises again. And the same thing in the upper layers as well. The temperature seems to be flipping and changing. Why do you think that is the case? Okay, why? I'm not going to quite answer for you. Okay, I want you to do some research and figure out why that's the case. Maybe don't. Just based on what we learned so far, okay, why do you think the temperature changed the way it does? All right, finally, the one I jumped ahead earlier is our system. The last system sphere we're going to study, which is the hydrosphere. Hydrosphere, it accounts for all the water on Earth. Okay, all the water, salt water, fresh water, lakes, rivers, streams, glaciers, etc. And ocean, rivers. I already mentioned rivers, and technically also the clouds in the sky. They're water. They're not air. Okay, the clouds up in the sky, they're all part of the hydrosphere. Okay, because without the clouds, without the rain, there wouldn't be any exchange of energy for the other systems. They're part of the water cycle. 97% are salt water. We cannot drink those. We have to treat them with a lot of processes, okay, which require a lot of energy. Okay, in order to drink those. The water we definitely can drink, which require less processing power, it's only 3%. So like I said, most of Earth is very hostile to our way of life. So that's why we need to take care of it. Okay, because if we don't, we're going to lose even more of that. Anyhow, I digress. Hydrosphere covers 70% of Earth's surface. You might remember I said atmosphere is the biggest part of the Earth's biosphere. I didn't lie. Okay, but the atmosphere floats on top of the Earth's surface. It's not on the Earth's surface. Okay, it covers 100% of the Earth's surface if you want, but that's not what we're talking about. It's above. On the surface, the lithosphere is only 30%. 70% is Earth is covered by water. Okay, on the surface level. The frozen water is also, we usually give a name. So the ice chunks, okay, we usually call them the cryosphere. Okay, but we count them towards part of the hydrosphere for the purpose of this course. 23% of the sun's energy is used to move these waters around in the hydrosphere. Okay, turn them into cloud, ring droplet, and then evaporate them again. All these uses up about 23% of sun's energy and a little bit of the Earth's energy as well. Okay, so it is a huge part of our energy exchange. So this is the water cycle. Okay, hopefully don't have to say. Rain, sun, the source of everything. Like this, what powers the Earth is the same thing that powers. I'm going to do a slight tangent here. Superman, right? Superman is powered by the sun. The Earth is also powered by the sun. The sun will evaporate the water on the air, on Earth. They'll condense into cloud condensation. You condense into clouds, and then the clouds are going to move in the atmosphere, okay? But then it's going to precipitate somewhere else, transfer the energy from here, transfer water over there, and then gravity going to pull this water back down, forming a cycle, a circle of life, a circle of water, but also a circle of life. This creates a lot of energy transfers, which helps improve life. Okay, well, help life develop. So that is the hydrosphere. It's fairly simple. You have studied it before. Okay, and then of course when biosphere interact, temperatures and weather is going to change. Okay, as biosphere interact. The simplest example is rain. There's temperature from the atmosphere. There is of course water and cloud from hydrosphere, and it lands on the ground, right? So it involves everything. Temperature and weather are all impacted by everything. The biggest impact is altitude, at least in the troposphere level, especially in here, but also in other levels. Generally, we measure altitude. Altitude is height from sea level. So distance from sea level. Okay, that's what I mean by altitude. So an altitude of 5 meters is 5 meters above the average sea level. Generally, as we study, or since we're sticking with the troposphere, so as altitude increases, temperature decreases because sticking in the troposphere. And the area near mountains, though, there's something strange could happen. Is when the cool air didn't get properly released into the upper, and the warm air from the side of the mountains got trapped into the ground. Okay, the warm air really is actually what's trapping it. The warm air form a trap and traps the cooler air in between the mountains and create a process of the temperature inversion. Like these happens. Okay, generally yes, it gets warmer as it gets higher, but something strange like this could happen. So this is what really happens. So normally, if you look at the top picture here, normally warm air is on the bottom. You remember from the physics unit. Energy transforms from warm to cool. So warm air will transfer energy up and away. So all the energy is floating this way. Energy is floating this way in the form of heat. So warm air transfer energy tops air. So in a sense, air is floating upwards, right? That's normally what would happen. Okay, so all the air down here gets released up, and the cooler ones, of course, will fall down, circling, so refreshing the air. You can think of sort of like an air cycle, I guess. But if the ground level is cooler, so like this one, ground level is cooler, and there's a warm layer trapped in the middle, remember, energy always flow from warm to cool. So the energy now flows this way. Of course, the upper side is fine. That's fine. But the bottom side, that's how energy is flowing this way. So this cold air will never escape. The cold air get trapped inside, warmed up, and fall back down. So the air inside gets trapped. It never gets refreshed. Okay, you'll never go past the warm layer. So all the air get trapped. Now, what's the issue with that is, as air is trapped, pollutants can also become trapped. Right? The pollutants are part of the atmospheric particles we talked about earlier. They can be trapped along with the air if you got trapped. So that does create a problem for temperature inversion. So that's why also we need to watch our pollutant releasing pollutants, especially in mountainous areas. Okay, so that is our biosphere in a nutshell. Okay, here are some questions in your textbook you could try if you are using the Science 10 textbook by Addison Wesley from Pearson's. But if not, this question probably won't mean anything to you. But this is our Earth's biosphere in a nutshell. Next, we'll take a look at some climate and weather-related stuff and how some basic studies on them before we jump into a closer look at each of our biospheres and how they impact our climate and weather. And ultimately, we'll finish up this topic about our biosphere, about our Earth, with a study on climate change. And with that, thanks for watching. Have a good day.